Okay, so this is section 2.5 continued. So the differential equation dy dx plus pxy, so p is a function of x, equals some function of x times y to the n, where n is a real number, is called a Bernoulli equation. Okay, now we're going to look at a theorem on how we can solve these Bernoulli equations. So theorem 4, so let me write theorem 4 now. Okay, so here's theorem 4. It says the substitution u equal to y to the n minus 1 power reduces the Bernoulli differential equation to a linear differential equation. So let's prove that. So proof. Okay, so proof, we're going to let u equal y to the 1 minus n power. We're going to now substitute into this differential equation above and show when we do that it turns into a linear differential equation. So to do that we're going to have to substitute my dy dx and my y in terms of u. So let's first solve this guy for y. So to do that we're going to raise both sides to the 1 over 1 minus n power. So doing that we get then u to the 1 over 1 minus n power equals this guy here. These will cancel because you multiply the exponents. So doing that we get then y equals u raised to the 1 over 1 minus n power. We are dividing by 1 minus n here, so for this analysis I'm assuming that n is not 1, otherwise you'd be dividing by 0 here. But if n was 1, then this would actually be separable, so there's no need to, wouldn't be any need to worry about it in that case. So we're assuming that here that n is not 1, okay, for the time being. So we have then y equals u to the 1 over 1 minus n power. So I can make that substitution for the y here and here, but let's take derivative of both sides with respect to x then. So doing that we get, so taking derivative with respect to x, so derivative of this guy here, derivative of y would just be, with respect to x, would be dy dx, and derivative of the u guy raised to the 1 over 1 minus n power. We take the power in front, which I've done, then subtract 1 from the power, then multiplied by du dx by chain rule. And we can write 1 as 1 minus n over 1 minus n, so let's do that. Okay, so I added the 1 over 1 minus n minus 1, so the 1 you can write as 1 minus n over 1 minus n, then the minus sign will distribute there, and the ones will cancel and just become n over 1 minus n. So substituting up here then, the dy dx guy becomes 1 over 1 minus n u to the n over 1 minus n du dx. Okay, so now I'm going to substitute in place of dy dx up here, I'm going to substitute this guy, and in place of y here and here, I'm going to do that. Okay, so doing that. So again, we're going to substituting in place of dy dx, we're substituting the 1 over 1 minus n u to the n over 1 minus n power du dx, and in place of y here and here, I'm substituting the u to the 1 over 1 minus n power. Okay, so I'm out of space, so I'm going to erase a few things and I'll make that substitution and we'll keep going. Okay, so after making the substitution, so again here's the original differential equation, here's our substitutions. So making those substitutions into this guy over here, we get this new differential equation. And I want to show this new differential equation is actually a linear differential equation. So let's multiply, I want to get rid of this u term in front here. Let's multiply both sides by u to the minus n over 1 minus n, and also by 1 minus n. So let me write that over here. So we're going to multiply both sides by 1 minus n u to the negative n over 1 minus n. So I want to get the du dx term by itself here, the coefficient in front to be 1. So doing that we get, alright, so multiplying everything by 1 minus n u to the minus n over 1 minus n power. Put down to here, here, and here. And this guy here, this n, being multiplied by the 1, so this is just going to be u to the n over 1 minus n, which I have here. That's multiplied by this guy. We got the 1 minus n in front here. So simplifying this, well, these cross off here. And when you add those exponents, there's going to be u to the 0, which is 1. That's going to be u to the 0 also over here. And that's going to be, adding the exponents here will be 1 minus n or 1 minus n, so it's just going to be u to the 1. Let me write that down here. Simplifying then, we have u to the 0 du dx plus 1 minus n px times u equals 1 minus n fx u to the 0. U to the 0 is 1, so let me write one more step here. So we get this, and then we just need to realize that this is a linear first order differential equation in u. So you could call the 1 minus n px, you could call that, say, p tilde, and you can call the 1 minus n fx f tilde. So let's do that. Okay, so making those substitutions, then you'll have our du dx plus p tilde u equals f tilde. So note, this is a linear differential equation now. So we've proven the theorem, so we're done. So we're done with the theorem. Okay, so we'll do an example in the next video. So let's leave this video here then.